Hello all, welcome to this new lecture on Vehicle Dynamics and Electric Motor Drives course. So we have discussed so far about the DC motor control, some of the modeling for the induction machine, basics of that, and pulse width modulation techniques. Now in this lecture we are going to continue with the modeling and control, particularly dynamic modeling and some of the advanced control techniques for the cylindrical rotor machines. So let us proceed with the basic structure of the motor drive. During one of the lectures, we have seen that motor drives essentially consists of power converter, which I am representing by this symbol, which is providing power to the machine. Since we are going to deal with AC machine, so I am drawing three-phase output from the inverter. The machine is connected to a load, and there is some rotational speed omega m involved with that. Now, typically, when we are talking about a drive structure, this is the hardware that is involved with the complete system. To operate this hardware, we need another block which we can call as software, which is essentially part of a control board. Now, the task of control board is to understand what reference input is provided to the system, and based on the feedback, which is electrical and mechanical in nature, it provides the operating command to the inverter, which basically drives the motor. Now, the software which I am referring to is basically, it could be a program or could be a model written on some Simulink based system. So it depends essentially on the type of system what we are dealing with, and the requirements what we have from the system. Now when I say type of system, what basically I mean is, what is the type of machine involved over here, and what is the power converter involved over here, and also the mechanical dynamics involved with the motor and load. So in other words, we basically need to have mathematical model for the whole system. So we need good understanding about the whole system, and which is why we need to have mathematical model, which essentially consists of electromechanical model of motor plus load and electrical model of power converter. So what we will do over here is that we will take these two parts as the task for this lecture, and we will try to model the machine which we are going to deal with. Now the type of machine we have seen in one of the lecture, there could be many types of machines, but here particularly we are going to deal with cylindrical rotor machine, or also called as symmetrical rotor machine. So a typical structure of the machine can be seen here. So during one of the discussions in induction motor lectures, we have seen this structure. So when I am calling symmetrical rotor structure, I essentially mean that the rotor is symmetrical about the rotor axis. So if we travel at any angle, say theta, from the reference axis, the rotor structure is uniform around that. So this is what is meant by cylindrical rotor or symmetrical rotor. Now, when we see this structure, what we have basically on the stator, we have slots provided for keeping the stator winding, which is distributed in nature. And when we talk about rotor, there are several options what could go over there. There may be distributed winding, same as the stator, or there may be rotor bars, as we have seen in case of a squirrel cage induction machine, or there may be permanent magnet in case of permanent magnet synchronous motor. So we are taking a general case of such machine and we are trying to model. First we will see the equivalent circuit, how it can be drawn, and then we will go for the mathematical model of this structure. Now, going ahead, if we want to draw the equivalent circuit for this machine, we again need to refer to one of the previous lectures where we are trying to see this machine as transformer. So there windings on the stator and rotor side are isolated and we are providing supply possibly from one side or in general from both the sides. Now what we have done earlier is that we have kind of developed an equivalent circuit which essentially consists of resistance and leakage inductance element on the stator side, a magnetizing branch which is the common link between stator and rotor, leakage on the rotor, and resistance on the rotor side. In general, the winding may have possibility, the machine may have possibility to receive supply from both the ends, which is why the terminals on the stator and rotor side are open. Current flowing on the stator and rotor side are also marked over here, and the magnetizing current IM flowing in the magnetizing branch is also indicated by IM. Here IM is equal to IS plus IR. We have followed the convention to supply the rotor current into the rotor direction, and which is why we are able to write IM as sum of IS and IR. Now if we proceed further, because we are dealing with multi-phase machine, and in particular we are going to see three-phase machine. So essentially what we are trying to say is that we are going to have three per phase circuits symmetrically placed for R, Y and B phases. Now if we try to write the equation for this system, we need to write equations separately for RYB. That is one way of representing this machine. The another way of representing this system could be if we can unify the three-phase system into, say, one unit, and this is where we go on and refer these multi-phase quantities in terms of space vector. So what we will try to do, we'll use the concept of space vector to represent our multi-phase quantities as a vector rotating in space. So to understand how this is going to happen, so I have taken example of say three-phase system where in particular we can take RY and B phase. Say we are considering the voltage over here, so we can take VR, VY and VB, and what is suggested basically is that these are distributed in time to have a balanced three-phase supply. Which means that at any point of time, sum of the three quantities is going to be 0. The scalar sum of all three voltages is going to be 0. However, the notion of space vector suggests that we are not seeing these quantities as a scalar quantity, but these are seen as vectors which are placed in space at uniform positions. So for example, if we talk about R phase VR, so we can consider this horizontal axis along which VR is placed. So I can say this is R phase axis and VR can be placed say at this point. Now what it means is that when we are having voltage given as Vm sin omega t, it can change its magnitude anyway from plus Vm to minus Vm. Now when we are placing this vector, and please understand this is not the phasor which is rotating in space, this is a vector which is placed in space. It can change its value from plus Vm to minus Vm along this axis, which means that if we are marking this position as Vm, the vector can take any value on this axis between plus Vm and minus Vm based on the value of omega t. Similarly, when we are talking about Y phase and we have the distribution in time sin omega t minus 2 pi by 3 appearing over there, we place the vector 120 degrees shifted from the R phase, something like machine winding. So along this axis, this can be considered as Y axis, and once again our vector can assume any magnitude from plus Vm to minus Vm. So this is our positive Y axis side and this is negative Y axis side. So vector cannot change its position, it can only change its magnitude along the axis. That is the representation given to it. Similarly, when we are talking about B phase system, Vb is given by Vm sin omega t plus 2 pi by 3, we'll place it again 120 degrees shifted from the Y axis. So this is the axis for B phase and this is the positive side we are having, and then our vector Vb can take any value from plus Vm to minus Vm. Now what happens when we are placing these quantities in space as a vector, we are representing it with a magnitude and then with a associated direction. So I would write Vr as a vector. So underscore is the notation for vector in this course, and we are writing Vr as the magnitude Vr times of the unit vector associated with the position. So in this case, this theta is basically 0 degree for R phase. This is our reference axis, which is why I can directly write 0 degree over here. Similarly, when I am writing Vy vector, I will write the magnitude of the vector which is Vy, again varying with respect to time. However, position is 120 degree from the reference axis in the counterclockwise direction. So I can write e raised to the power j 2 pi by 3, which is a positive number, and then similarly for Vb, the magnitude of the B phase vector, and then the angle formed by this vector from the reference axis, which is 4 pi by 3. Now, when we have these three vectors placed over there, it can be seen that if we try to add these vectors, Vr plus Vy plus Vb, these will not add up to 0. For example, if we take an instance, say at 90 degree, the position of Vr is at plus Vm, say at this point. However, the position of y and b is at minus Vm by 2. So which means that y is along the negative side and having a magnitude of minus Vm by 2. B is also along the negative side having a magnitude of minus Vm by 2. Now if we try to add these three vectors, it is going to give us a resultant vector which is going to have a magnitude of 3 Vm by 2, and it is going to be aligned along the R axis. Now if we move from this point, this omega t, to another point, say place where y is having the highest value, what we are finding is that the vector Vy is having a value plus Vm, and R and B are having a value of minus Vm by 2 on the negative side. So R and B both have minus Vm by 2 values. So this is for the condition when we have omega t equals 120 plus 90 degree. So now what we find that adding vectors which are coming at this position, it gives us a vector which is aligned along y-axis and having a magnitude of 3 Vm by 2. Similarly, if we go for another position where B phase is having the maximum value, the vector is going to be aligned along this B axis and it's going to have a magnitude of 3 Vm by 2. So what we find that this vector, which we can in general call as the voltage vector Vs, which is net sum of these three vectors. So here this is what we mean by the net sum. This vector is actually rotating with the speed omega on this circle, and it is having a magnitude of 3 Vm by 2. So this is what a multi-phase quantity, or in particular three-phase quantity, what we are discussing. It is kind of representing, or it can be represented in terms of a rotating vector, which is combination of all the three phases. So we can write it more formally what it is going to be. The vector Vs, and if we replace the values of Vr vector, Vy vector and Vb vector, now opening this unit vector, we are going to get these real and imaginary components. So in general, any vector, as we understand that, can be represented in a plane by using two orthogonal components. So what we have essentially drawn as our reference axis, we can call this as the real axis, and then we have the orthogonal axis, which we can take as imaginary axis, and we can name these real and imaginary axis as, say, alpha and beta. Now, by naming these alpha and beta, we are essentially calling the components along alpha and beta as Vs alpha and Vs beta. So this vector, voltage vector, can be represented in terms of two components, Vs alpha and Vs beta, where Vs alpha can be computed from this expression. For a specific case where we have some of the three voltages, scalar sum of the three voltages going to 0, which means a balanced supply, we can always write it as 3Vr by 2. And V beta can be written by root 3 by 2 times of Vy minus Vb. Or if we plug in the values of sin omega t minus 120 and so on, we are going to get ultimately so as I suggested, the magnitude of the vector is going to become 3 by 2 times of Vm, and there are two orthogonal components which are associated with this vector. Now, once we have this understanding that this voltage can be represented in terms of a space vector, the same can be repeated for any other three-phase quantity. For example, we can similarly write the current vector, flux vector, and so on as and when required. Now, if we go back to our circuit and we try to write the equation for this equivalent circuit, say we are writing for R phase, what we are going to actually do is we are going to write the KVL for the stator and rotor parts. Now, we can go by the approach that we can write individual voltage KVL equations for R, Y, B phases, or we can have a unified KVL for the voltage vector Vs. So going by the second approach, where we have a compact equation and a clear-cut representation, we are going to have Vs given by the vector Is times of Rs LLS times of Rs plus the magnetizing branch, which basically consists of both stator as well as rotor current. Now the problem that occurs over here is that we are talking about stator equation and we are dealing with the current which is on the rotor side. Now as long as we are talking about this T network, it is fine, but the moment we are referring to any machine where we have two parts, one is stationary, another is rotating with omega m, so our vector has to be represented properly in the frame of reference where we are writing the equation, which means that if we are writing the KVL for the Vs side and we are referring to any quantity which is flowing on the rotor side, we need to be careful in terms of representing the vector in the correct frame of reference. So at this point of time, what we will do is that we will take the frame of reference what we have considered for our voltage vector, and we will see how the rotor current vector can be represented. So for example, what is said is that we are having alpha beta frame of reference and we have represented our Vs voltage vector in that, so Is voltage vector also can be represented in that. Now when we are dealing with machine and we have rotor where windings are located and current vector IR is represented in that, we essentially say that there is a frame of reference alpha r beta r attached to the rotor with respect to which we are writing our current vector IR. Now, whenever we are going to change, which means we are going to refer to this quantity from a KVL in the KVL equation which is written in the stator frame of reference, we need to have correct representation of this vector. So, we should be able to write this vector IR in terms of this frame of reference alpha beta. And for clarity, we will write this frame of reference alpha beta as alpha s and beta s to make sure that we are referring to the stator alpha beta, and the other hand we have rotor alpha beta frame of reference. Now, I would introduce a term over here which can be called as native frame of reference. Now, the meaning of native frame of reference is that whenever we are dealing with any stator quantity, it has its own native frame of reference. Naturally, it is referred in that frame of reference, and that is stator frame of reference for any stator quantity, which means alpha s and beta s. Similarly, whenever we are talking about a rotor quantity, say current or voltage or flux, we are essentially referring it in the native frame of reference naturally, which is rotor frame of reference, and we have just now defined that as alpha r beta r. Now what is happening if I mention or mark the other frame of reference on the same plane? Essentially what is happening is that our frame of reference alpha r beta r is rotating with the speed omega m with respect to alpha s beta s. Say at any given instant it is making an angle epsilon, and this epsilon is related to omega m as d epsilon by dt is omega m. Now, if we are saying that we have the vector is given over here, and this is the natural representation, which means that the quantity which is a stator current is represented in its native frame of reference, which is alpha s beta s, then I need to find a way to represent is in alpha r and beta r. So I am looking for axis transformation or reference frame transformation. Now, what it essentially means is that whenever we are defining a vector, we are having the projections made by that vector on the axis of that reference frame. So in this case, it is is alpha, is beta. What I am trying to do now is basically to get the components of is falling on the alpha r and beta r, which I can write as is alpha r, is beta r. So to make it correct, the previous one I can write at is alpha s, is beta s. Now, of course, we are referring to the same vector. We are not changing the vector. We are only changing the frame of reference, which means that is alpha, is beta this is how we are representing the vector in alpha s beta s frame of reference. Now I cannot write alpha s again as is alpha r plus j is beta r. So there has to be something different on the left hand side to make sure that we are referring to the correct frame of reference for this vector. So this is where it is recommended that whenever we are changing the native frame of reference, we'll use a superscript to represent that. So if I am representing my stator quantity in rotor frame of reference, I would mention a superscript R. So this would essentially mean that stator current referred in rotor frame of reference. Whereas the IS vector simply means that stator current referred in native frame of reference, which is stator frame of reference. We can mention the same for rotor current as well. So if we are writing rotor current as IR without any superscript, we essentially mean that this is rotor current in native frame of reference, which is rotor frame of reference. Whereas if we are referring to this vector IR in a stator frame of reference, I would use a superscript S and I will write this is rotor current in stator frame of reference. So at present we have only two frames of reference for referring to these quantities, which is why it is okay to use superscript which is referred to these particular frames of reference. Now, which means that for this particular case, we are looking for ISR, which is essentially IS alpha R plus J IS beta R. So one way is that we can correlate the components IS alpha R, IS beta R with IS alpha S, IS beta S by using this angle epsilon and then projecting the vectors, projecting the components of that. In a compact manner, what we can say is that if we are changing our frame of reference, say for example, our quantity is IS, which is naturally referred in alpha S, beta S, and we are changing that frame of reference to alpha R, beta R, which means that from alpha S, beta S, we are moving to a frame of reference which is in the counterclockwise direction at an angle epsilon. So we can write in a compact manner ISR, which is the new vector in the different frame of reference, as the vector in the old frame of reference which is known to us times of unit vector multiplication, which is nothing but equivalent to the angle formed between these two frames of reference. So we have IS vector represented in or referred in rotor frame of reference given as the vector IS in the native frame of reference times of unit vector, and please note the sign over here. Whenever we are going for counterclockwise direction, I am placing a negative sign. So component wise derivation is also going to match with this transformation. So it is up to the students and the candidates to verify this on their own and see that if it is correct or not. Now, given that I have represented the vector IS in rotor frame of reference, if I know the vector in its native frame of reference in this manner, I can do the reverse also, which means if I know the vector in the rotor frame of reference, I can multiply the unit vector and I can get the vector in the original frame of reference. So this is just an illustration of what we are doing over here. Similarly, for the rotor current vector also, we can represent the rotor current vector in a stator frame of reference by having the product of current vector in the rotor current vector in the rotor frame of reference and the unit vector which corresponds to the angle made by original frame of reference to new frame of reference, which is actually now minus epsilon. So which is why I have placed a plus epsilon over here. So this can be used to now correct my equations which are written over here. If I am writing this KVL for the stator quantity, inherently I am writing this KVL in stator frame of reference, which means that the rotor current vector IR cannot be written without any superscript. There has to be a superscript for representing that it is a quantity from a different native frame of reference. Now, similarly, we can have the KVL for the rotor side, where again the current vector IR, voltage vector VR, these are given, and when we are writing the rotor side KVL, we will be writing it in the rotor frame of reference. And once again, because there is magnetizing branch which consists of both the currents, we are going to have IS vector represented in the correct frame of reference. So these are my equations, and we need to be sure that these two equations are written in two different frames of reference, which is why we have quantities given with a superscript which are appearing from a different frame of reference. So we can plug in the expressions derived for these transformations, and we can simplify the equation in terms of the rotor angle. Now this term coming over there, LLS plus LM, this can be taken together because both involve the stator current only, and there is another component associated with LM which is basically relating the rotor current with suitable transformation. So the term L plus LM, this can be combined together to be written as the total inductance, or in particular total stator inductance. Now this equation can be written in further compact manner. Similarly, we can derive the rotor side equation, and we can write in this form. Once again, it must be clear that equation 4 is in stator frame of reference, and equation 5 is in rotor frame of reference. So what we find over here is that for a general cylindrical rotor machine, we essentially have two equations which are in vector form, and these are relating to the quantities which are on the stator and rotor side, and based on the specific need for a particular machine. For example, this general equation can now be taken in different forms based on what type of machine we are dealing with. So most general form is basically when we have windings on both the sides, which means stator as well as rotor, and there is possibility of providing supply from both the sides. So such kind of machine is wound rotor induction machine, which will basically correlate to these both equations. We need both the equations to solve for having the control of this total wound rotor induction machine. Whereas if we talk about permanent magnet synchronous machine or induction machine, the rotor side equation has to change. So in case of PM, there is no rotor side circuit. In fact, there are magnets on that, which means that VR equation becomes useless for us. And then because there is current component coming on the stator equation, we need to take care of that. Similarly, when we have induction motor, we are saying that our, particularly the squirrel cage induction machine, when we are talking about, we are saying that we have rotor bars placed instead of winding. So which means that we are not having any voltage on the rotor side. It is shorted from both the ends, so we don't have possibility of any voltage. However, the current, so we don't have any voltage available, which means VR is 0. However, the current is flowing in the rotor circuit, so current is non-zero. In that case, again the rotor side equation is going to be modified. So which is why this generic equation, then generic model for machine, symmetrical machine, can serve purpose for all such machines which are falling in this category. So going ahead, we are going to deal particularly the PMSM and induction motor in this course, squirrel cage induction machine. Wound rotor would not be part of this course because this is more related to electric vehicles. So here what we will do, we will now take the specific cases of these machines, PMSM and squirrel cage induction machine, and we will use our generalized equation to derive the dynamic equations of these machines, and then we will develop the suitable control techniques for which is going to be applied to these motor drives. So see you all in the next lecture. Thank you.